Dear students, in the last session, we observed what is a tree and properties of trees. Next, at the end, we observed this definition, minimally connected graph. So when we can say that a connected graph is a minimally connected graph, okay? If the removal of any edge from the graph results the given graph into disconnected graph, then we call it as a minimally connected graph. So what is the use of this definition in trees? So to check whether the given graph is a tree or not, mainly you have to check that connectedness. Okay, a connected graph is a tree if and only if it is minimally connected. So you have one important point here. The help of this minimally connected graph, you can write this statement like a connected graph is a tree if and only if it is minimally connected. Okay, so you observe minimally connected graph we are saying now. See this, if you have the graph that we have taken in the previous session also. So this one V1, V2, V3. So this one is the graph we have taken previously. So this is G. So by removing any of these edges, definitely it will be a disconnected graph. But if you add an edge, okay, if you add an edge between any pair of vertices here, it results a graph as cyclic graph. Okay, there exists a cycle in G if you add any new edge here. Okay, so definitely this is one useful result to check whether the given graph is a tree or not. So first you have to check it is connected, and if it is minimally connected, then definitely it is a tree. Okay, so if you observe this graph, so if you remove any one of those edges, so if you remove the same E1 here now, so then definitely see this V1, V2, V3, V1, V2, V3. So here I am removing this E1, then V2 and V3, if you observe, there is an edge between those two, and between V1 and V3, there is an edge. Okay, E2, E3 are there. So now you observe this is a connected graph. Connected graph. Okay. So, but this is not a minimally connected graph. So by removing an edge, you are getting a connected graph only, not a disconnected graph. Okay. So this is not a minimally connected graph. So if you want to say a connected graph is minimally connected by removing one edge, any one of the edge from that, so you will get disconnected graph. Okay, so that is the point that you can write based on that minimally connected graph. Next, you observe here the new one, directed tree. In the previous session, we observed what is a tree. Now we observe directed tree. So in the name itself, you have directed tree. So here I am taking a directed graph. A directed graph. So here I am taking the directed graph like D. I am representing with the D. V comma E is said to be a directed tree if the underlying graph, undirected graph G of D is a root. Sorry, is a tree. Sorry. It is a tree, not a root. So is a tree. Okay, a directed graph dv comma e is said to be a directed tree if the underlying undirected graph G of T is a tree. Okay, so you observe if you have some directed graph where there is an importance for the direction between those vertices. If you are joining those vertices, so D here I am taking like this. This is a directed graph with these vertices A, B, C, D. Okay, is it a directed tree? So for this, we have to take the underlying undirected graph from this. That one we are calling it as G. So how it will be? See this? This is only the, so don't consider the direction of those edges here. So draw that undirected graph that we obtained from that D. Okay, see this. Here, is it a tree? If G is a tree, then you can call D as a directed tree. Okay, but here G is a connected graph, no doubt in that, but G is having cycles. Okay, it is having cycles. So it is not a cyclic graph, it is having cycles. So it is not a tree. Okay, G is not a tree. So D is not a directed tree. It is not a tree. Okay, cycles are there. So it is not a tree. So you observe. So some other directed graph. So this is also having how many vertices? 4 vertices. This is a directed graph. Now underlying undirected graph for this graph I am taking. So this is also having 4 vertices A, B, C, D. This is G now. Okay. So here join those vertices in the graph with undirected edges. So this is underlying undirected graph for this directed graph. Now you observe G is connected. Yes, this is true, connected. And there are no cycles in this graph. So what you can say from these two, G is a tree. G is a tree. So since G is a tree, so this D is a directed tree. Directed tree. Okay. So now after observing what is a directed tree, we will go for a rooted tree. So we will go for that rooted tree. Sorry. So now here I'm taking first a directed tree. A directed tree So I'm representing like T is called a rooted tree, if first point here T contains a unique vertex, okay, this is important, a unique vertex whose in degree is 0, and the second point, the degree, degree in the sense here in degree of all other vertices is 1. Okay, so you know degree of your vertex. So if it is a directed graph, so for every vertex you will have in degree and out degree. Okay, see this here. I'm taking some directed graph. Okay, so here the vertices are like A, B, C, D. So concentrate here to observe that what is in degree and out degree of your vertex. So here for the vertex B mainly, it is easy to you to follow. So for the vertex B, what is the in degree of vertex B? Okay, or simply ID of B. So for how many edges the vertex B is the terminus or terminal vertex? Okay, so those many edges will count for this in degree of B. Okay, so you observe it is not the initial vertex terminus for this edge from A to B. Okay, so in degree in the direction also you can observe. So this is 1. Okay, so you can represent like this is D minus of that B degree in degree. So it is 1. Okay, so out degree. So what is out degree here for B? So for how many edges the vertex B is the initial vertex. Okay, that is the starting vertex. So here for how many vertices it is uh, like a initial vertex for two edges. So this is out degree of B. For A, what is the in degree? Okay, so for any edge you observe here, A is not an terminal vertex or it is not a terminus. So the in degree for A, it is in degree for A, it is 0, and out degree for A, it is 1. Okay, for one edge here, A is the initial vertex. So out degree of A, it is 1. Like that for any vertex in this directed graph, you can write. Now you come to this definition. A directed tree, T is called a rooted tree. You know directed tree, just now we discussed. So next, when you can call it as a rooted tree? If you have some specific vertex in that tree, okay, tree is nothing but a graph only, so you can call a vertex, so whose in degree is 0. So only one vertex like that you must have. Next, for the remaining vertices in that tree, in degree is 1. Okay, so then you can call it as a rooted tree. So now after observing this rooted tree, here we will observe some other terminology in the trees. Okay, so generally we will represent rooted trees. Okay, so in the form of some levels. So first we are saying there exists only one vertex as a root. Okay, so for example, you take the vertex V as a root. So the vertex which is having the in degree of that vertex as 0, we call it as a root node. Okay. So next, from this root node, you observe in a graph or in the tree. Okay. If there are any vertices that are reachable from V of the path length 1. Okay. So adjacent vertices for V. Okay. So the path of length 1 means only one edge, okay, that are reachable from V. You have to take in the next level, So below that V, you have to add those vertices if there exists any vertex like this. Okay. So join those vertices. I am aiming at like A and B. Okay. Actually, the level of this root node or root vertex, we call it as it is at the level 0. This is for level 0. And these vertices which are reachable from this vertex V, we call them as those vertices are at level 1. Level 1. Okay, from the root node, you are having a path of length 1. So these vertices are of reachable from V, and the path is of length 1, like that. Next, from V, okay, vertices that are having a path of length 2, we have to take in the next level, or you have to take the vertex A here. So next, you have to add the vertices that are reachable from A, okay, not the root vertex, reachable from A, okay, and you have to take those vertices in the next level. So if you have some vertices like this, so join those vertices C and D. If you observe this C and D, they are also reachable from V, okay, but it is of path length 2. Okay, two edges are there to reach that C from V. Okay, one edge only there from A to C. Okay, so like this. From B also you check and you add those vertices in the next level. So observe C, D, E, F, G, all these are in the next level, level 2. Okay, so like this, we continue adding those vertices from these vertices that we have in the level 2, so to get the vertices in the next level. So some other vertices here, so maybe V1, V2 like this, and the vertex, only one vertex here I am taking like V3. So some vertices V4, V5, okay, maybe only one vertex V6. See this from G, V7, V8 like this. All these are at level 3. Okay, so you observe here these vertices V1, V2, V3 and so on up to V8 we have now. What is the out degree of these vertices? Out degrees of these vertices? Out degrees are zeros and in degrees are 1. So if the out degrees of these vertices are zeros, okay, so we call these vertices as leaf nodes, leaves, okay, leaves are leaf nodes of the tree, leaf nodes. This is the root node and all these are leaf nodes. Leaf nodes, okay, and the remaining vertices which are in the middle levels, so these are all called as internal vertices. Internal vertices, okay. So how you can differentiate which is a leaf node or internal vertex? So you observe here for a internal vertex, so you are having out degree a like either 1 or 2. Okay, out degree is either 1 or 2. So then you can call it as a internal vertex. But if it is a leaf node, so it is mm, you observe it for these vertices. So the out degree of these vertices is 0. Okay, only you are having in degree. Okay, so you have here a root node, internal vertices, and a leaf. So next, some other terminology. Okay, so observe here from A, observe A and C. Okay, so here we call A as parent node for C, parent of the vertex C. Okay, and C is called the child of that vertex A. C is the child of A. Okay, here D is also a child of A. E, F, G are the children of B. Okay, E, F, G are the children of B. Okay, so here C and D are called. So these are the children of the same parent. Okay, A. So here we call them as siblings. Siblings. Okay, C and D are siblings. Okay, so next, yes, descendants. Descendants of a vertex. So if you have some vertex, for example, you take the vertex A. What are the descendants of A? Descendants of the vertex A are nothing but the children of A and the next children of that C and D for this. So the set of all those children of A, that is C comma D, and the vertices in the next level like this, up to those leaf nodes, you have to list V1, V2, V3, means children of A and children of their children, like that you are taking. So these are all called as descendants of the vertex A. Okay, next, if you observe, so for C, you know, A is the parent node. Next, if you observe, maybe for V1, vertex V1. So here A is called ancestor. Okay, ancestor. For V1, C is the parent and A is the ancestor, like that you can take. Next, height. Height of a tree. Height of a tree, not a root. So it is height of a tree. So our level of a vertex, like that we have some terminology. So what is the height of a tree? So that is nothing but it is defined as the maximum level of any vertex that we have in the tree, a rooted tree. So height of a tree. So mainly it is a rooted tree. So this is nothing but the maximum level of any vertex that we have here. The maximum level of a vertex in a tree. So you observe here, what is the maximum level we have here? Okay, 3. So height of this tree is 3, maximum level that we have in that tree. So only one vertex you have at this level. So in that case also, we'll call the height of a tree is 3. Okay, so next, another one, depth of a vertex. Depth of a vertex. This is only for a vertex, not for a tree. So what is the depth of the vertex C here? Depth of the vertex C. So that one, for writing that, you have to check what is the length of the path from the root node. So what is the length of the path from this root node? So the path is like V to A. Okay, A to C. There exists only one path because it is a tree. Okay, not more than one path. So what is the length of that path? You have to check that the length of the path from the root node to that vertex is nothing but what is that? Depth of a vertex. Depth of a vertex. So height of a tree, depth of a vertex. Okay, so the length of the path from the root node of that to that vertex is called as a depth of a vertex. Depth of a vertex C is 2. Next, depth of a vertex V is 3. Depth of a vertex B is 1. Depth of a vertex F is 2, like that. Here E, F, G are siblings. So the terminology is, you must know, that is important actually. Okay, so they may ask, write about rooted trees and write about what are the siblings, what is the height of a rooted tree, and what is the depth of a vertex, like that. So they may ask like some bits also for essay question, even they may ask. Okay, so then you must know all these points. So what are internal vertices? When you can say that a vertex in a tree is an internal vertex, internal vertex. So you observe, if the out degree of that vertex is 1 or more, then definitely that is a internal vertex. Or you can say that, so for any vertex, if you observe, there exists 1 or more children. Okay, 1 or more children, then definitely that vertex will be a internal vertex. That vertex will be a internal vertex. Okay, so next. Now we observe the definition of binary tree. When we say that a tree, here we are discussing about now rooted trees. Okay, when we say that a rooted tree T is a binary tree. When we say that the rooted tree T is a binary tree. So here first I am taking a rooted tree. A rooted tree T is called a binary tree if out degree of every internal vertex is either 1 or 2 or at most 2. So out degree of every internal vertex is either 1 or 2 or at most it is 2. Okay, so then it is called as a binary tree. So you can draw one simple example for that. Draw a binary tree. So this is the root node A, B, C, D, E, F, G, like this. You observe. I am joining these vertices. So here what are internal vertices? Internal vertices. These are what are the internal vertices in this rooted tree? Internal vertices are A, B, and E. Here C, D, F, G are leaf nodes. leaves, and R is the root node. So internal vertices out degree you have to check. What is the out degree of A here? Out degree of A is 2. What is the out degree of B? This is 1. Okay, what is the out degree of E? 2. Okay, so if you have a rooted tree, like out degree of that every internal vertex is at most 2. It may be 1 or 2 or at most to maximum 2. So then you can call it as a binary tree. Binary tree. So this is a tree which is a rooted tree, and it is a binary tree also. This is the simple example for that. Okay, next one. Next definition. Complete binary tree. So when we can call a rooted tree is a complete binary tree. When we can call a rooted tree is a complete binary tree. So when we can call a rooted tree is a complete binary tree. So in the name you have complete binary. So binary in the sense binary digit system like 0 or 1 like that. So 2, yes. So complete binary tree. So for binary tree, how we are defining? So the out degree of every internal vertex in a rooted tree is at most 2. It may be 1 or 2 or at most 2 like that you can say. So here a rooted tree. So here also we are taking a rooted tree. T is called a complete binary tree if out degree, same out degree only we are concentrating of every internal vertex in T is 2. Okay, see this. So I'm taking this is the root vertex A, B, join these vertices first, C, D like this. I'm taking next from this. I'm taking 2 more vertices from B. So what are internal vertices in this tree? It is a rooted tree, no doubt in that. Okay, what are the internal vertices here? Internal vertices. Internal vertices. Observe here, what are internal vertices? A is the internal vertex because it is having the children. Okay, D is also internal vertex. Next, B is also internal vertex. H. So A, B, D, H are internal vertices. Next, the C, E, F, G, I, J. They don't have any child. Okay, they don't have any children. Okay, so they are leaves or leaf nodes. Leaf nodes. Yes. So here for A, the out degree is 2. For D and B and H, for all these vertices, the out degree is 2. Okay, so if you have a rooted tree where the out degree of every vertex in that tree is 2. So you can call this tree as a complete binary tree. So what about the example that we have taken for binary tree? See this, in the definition itself, there is a difference. So it may have out degree, the vertex may have out degree like either 1 or 2 or at most 2 only, like that we are taking. Okay, so here B is having, what is the out degree of B? 1, not 2. So it is not a complete binary tree. It is a binary tree simply. Okay. So the next definition is balanced tree. What is a balanced tree? A rooted tree T of height H is called a balanced tree if if the level of each leaf in T is H or H minus 1. Okay, level of a vertex or depth of a vertex. If they are at the level of H or H minus 1, see that I'm taking the graph or the rooted tree like this. A rooted tree like this. Join these vertices. I'm taking one more vertex here also. So this is a root node A, B, C, D, E, F, next G, H, I, J, K. Okay, so here you know the level of that root node level is 0. So for this it is level 1. These are at level 2 and these are all at level 3. So then what is the height of this rooted tree? Height. Height is, that is represented with H in this definition. This is the maximum level of that vertex that we have. So in a tree that is 3. Okay, then H minus 1 means 3 minus 1, 2. Okay, so you observe the leaf nodes here. So what are the leaf nodes in this? Leaf nodes are G, H, I, J, K, and F. So observe G, H, I, J, K are at the level 3, yes, and F is at level 2. So this is the height, okay, and this is H minus 1. So definitely this is one example for that balanced tree, for balanced tree. Okay, so now we go for next definition, that is full binary tree. Full binary tree. For this, I'm starting with a complete binary tree. A complete binary tree is called a full binary tree. Full binary tree a complete binary tree of height h, okay, is called a full binary tree if the leaves of this tree, if you represent it as T, the leaves of T are at the level H. All the leaves must be in the level H. Okay, or that is depth of each leaf node is H. Like that also you can say. Okay, complete binary tree. Complete binary tree. So here I am taking an example. Complete binary tree we observed. Next balanced tree we observed. So this one you observe here. I am drawing very simple one. This is the root. A I am taking. Next B and C. Next these two join with B, and next these two with C here. D, E, F, G. So observe the leaf nodes here D, E, F, G. So what is the height of this tree? H. So this is of level 0, this is level 1, this is level 2. So H is 2. And all these leaf nodes are at the same level, are at the same level. So it is a full binary tree. It is a full binary tree. Okay. So we will continue next definitions and very important topics like BFS and DFS algorithms to find spanning trees. Spanning trees. Already you are having some idea about that DFS and BFS in data structures also. So that we will see in the next session. Thank you.